And then what I'm going to do here is go over to the, let me share the screen. God, I hope this works. Okay. All right, Tavoy, can you see that okay?
Yes, sir.
Right now?
Yep. Yes, sir.
Okay. Let me zoom out just a little bit. Or am I zoomed out all the way? No, okay. Tavoy, say something for me so I can see if I can hear you.
Yes, sir. Yep.
I don't hear you very well. How can I turn the... Wait a minute. How do I turn up the volume for a participant? He's not on mute. What do I want to do here? The what?
The computer volume is already increased.
It's already at 100%, it says.
Okay, and so I don't think you can increase it for a single participant.
Okay, Tavoy, if you need to ask a question, you're going to have to really shout. Okay.
All right, no problem.
Where is it coming out of? Like, where's the audio coming from?
What? I don't know. That's a good question.
It might not be coming from the computer. It might be coming from a
speakers.
You might be able to plug different speakers and see which ones you like cut up.
Say something now, Tavoy.
Microphone check.
Good. That's much better. Thank you. I don't know how to use this stuff, folks. Okay. Thank you, Jasmine. All right. Okay, I am recording. Let me go back to share the screen again. Then we'll start. Okay. Hopefully this won't be too terrible. All right, folks. So we're going to continue our discussion of the Solow model. And as promised, today's topic is really all about the stability of the equilibrium in the Solow model. What we refer to in the notes as transition dynamics. Okay, so we have taken a look at proposition 1 and 2. And in particular, proposition 1 established the existence and the uniqueness of the long-run steady-state equilibrium in the Solow model. Hopefully you guys recall, though, our definition of an equilibrium in a dynamic macro model doesn't just refer to a steady state, right? It refers to the entire time path of a system of equations or a system of variables as the economy kind of gravitates or converges to the steady state in the long run. So a lot of times we're not just interested in the fixed point steady state equilibrium, but how the economy kind of behaves as it's transitioning towards that equilibrium over the short run. So to take a look at the full equilibrium path then in the Solow model, we want to study its transition dynamics. So today what we're going to do is look at the transition dynamics that are implied by the key equation in the Solow growth model, and that's that fundamental law of motion for capital. And basically we have two essential questions here. Can we demonstrate that the economy is going to converge to this steady state level of capital per worker, K star, regardless of what the initial value of capital is, right? In other words, is the steady state independent of K0? And moreover, how can we, or if that's the case, then can we actually characterize how the capital stock behaves as it transitions to that equilibrium? Does it kind of cycle around the steady state? Does it converge monotonically to the steady state? Does it start to move more rapidly as we approach the steady state, or does it start to slow down? What do those transition dynamics actually look like? So hopefully we'll be able to answer those questions today. But before we do that, I think it's important that you guys understand some notation when it comes to stability and instability in a dynamical system characterized by a difference equation. All right, so let me introduce some notation here. So this is just going to be a math, so not the Solow model in particular. Let's assume that there's some variable xt where xt plus 1 is some function g of xt. All right, xt we'll assume is just a scalar, some real valued number, and g is a continuous and differentiable function that maps elements of the reals into the reals. All right, so a very straightforward, potentially nonlinear difference equation. G characterizes the mapping from xt to xt plus 1. We're going to say that x star is a fixed point of this mapping G if it satisfies the following. X star is equal to G of X star. In other words, X star is kind of the steady state or the fixed point of this equation, right? If you plug in X star for XT, what the mapping G spits out is the same value of X. Once we get to that fixed point, we know we've reached this kind of steady state position, right? So X star is the steady state of this difference equation. XT plus 1 is equal to G of XT. Everybody see everything okay so far? All right. This brings us to the Theorem 2 in the notes. All right, and I'm not going to write all this down because it's in the handouts. Consider the following nonlinear difference equation. Xt plus 1 is equal to G of Xt. And we're going to assume that we have taken as given some initial value of x, x0, that's given. And that G, of course, maps the reals into the reals. And let's suppose we've also identified x star as the potential steady state of this mapping. So it satisfies x star is equal to G of x star. Further, the theorem says that we're going to assume that G is actually differentiable in a neighborhood of x star. So we can take, this is an important thing. We need to be able to take derivatives of this mapping G from xt to xt plus 1 at least locally. That is within a neighborhood of the steady state. Finally, we're going to assume, so this is the big assumption for Theorem 2, that the slope of this mapping, that is the derivative of G, evaluated at x star, is less than 1 in absolute value. That's the critical assumption that is attached to Theorem 2. If we're willing to make those assumptions, then one can show that the steady state value x star of this nonlinear difference equation is what's called locally stable or locally asymptotically stable. Now, what does that mean exactly? It means that there exists some open neighborhood around x star. Let's call it B of x star. So this is an open set of values around x star, such that xt will converge to x star as t approaches infinity, as long as x0 is an element of B of x star. So a system or an equation is locally asymptotically stable And what that means is if you take some initial value of x that's within an open set or a neighborhood around the steady state, that the dynamics of the system are going to be such that xt will converge to x star regardless of what that initial steady state is, as long as it's close enough to the steady state. That's what local stability means, okay? Now, there's an important corollary that goes along with this theorem. If the conditions of theorem 2 are satisfied, and if G is continuously differentiable everywhere, and furthermore, if one can demonstrate that this mapping has a slope that is everywhere less than 1 in absolute value, that is for all x in the reals, then x star is actually globally stable, in the sense that xt will converge to x star for all initial values of x. You guys see the difference then between the assumptions that are attached to theorem 2 versus the corollary? For local stability, what is required is that the slope of the mapping from xt to xt plus 1 be less than 1 in absolute value in a neighborhood of the steady state. For global stability, what this corollary tells us is that actually the slope of that xt to xt plus 1 mapping given by the function g needs to be everywhere less than 1. If you can demonstrate that, then in fact, that particular difference equation will be globally asymptotically stable, meaning that regardless of what the initial value of x is, doesn't have to be just in that small neighborhood around the steady state, but anywhere on the real line, it will converge to x star in the long run. Now, it turns out that the Solow growth model doesn't satisfy all of the assumptions necessary for us to simply apply this corollary. So it's not quite that easy. I wish it were. However, we're going to prove this corollary here in just a second. And the methods that we use to prove it, we're going to apply to the Solow model. So even though the Solow model doesn't actually satisfy this assumption that G prime is everywhere less than 1 in absolute value, it is still going to be the case that the Solow model is globally stable. And we're going to demonstrate that by taking techniques from the proof of corollary 2. Okay, so let me go ahead and...
Sir, one question.
Yeah, Tavoy, go ahead.
Yeah, could you expound a bit on the importance of that assumption that the absolute value of the first derivative must be less than 1? Could you like expound on the importance of that assumption?
Well, it's the critical assumption. Without the slope of that mapping being less than 1 in absolute value, the dynamics of the system are going to be explosive rather than stable. I think actually, Tavoy, to answer, I don't want to dodge your question, but I think in proving corollary 2, I'm going to attach a small graph to it, and you'll be able to see that anytime the slope is bigger than 1, you're going to have a unstable solution.
Oh, okay.
Okay, so that the whole idea of the slope being less than 1 is really important for stability of the steady state. And you'll be able to see that graphically here in just a moment.
Okay, thank you, sir.
Yeah. Okay, so let me attempt here a proof then of corollary 2. Let's start by simply just writing the generic nonlinear difference equation. Xt plus 1 is equal to g of xt. Okay, now we've defined x star as the fixed point of this mapping, right? So let me subtract x star from both sides of our equation. So xt plus 1 minus x star is equal to g of xt minus x star. Now, since we have defined x star as the fixed point, we know that x star is equal to g of x star, right? So g of xt minus x star is the same as g of xt minus g of x star. Let me take the absolute value then of both sides of this equation. Absolute value of xt plus 1 minus x star has to be equal to the absolute value of g of xt minus g of x star. Okay, now here's the trick we're going to do. That's probably not obvious to the casual observer. We're going to use the fundamental theorem of calculus to figure out how to rewrite the right-hand side in terms of an integral, right? The right-hand side should just be the integral then of, well, what is the antiderivative of g prime? Remember, what we know is, our assumptions are about information about g prime, right? So I want to be able to put the slope of g in this equation somehow. So what is the g can be viewed as the antiderivative of g prime, right? So I can rewrite this as the integral from x star to xt of g prime of x dx, right? That's the fundamental theorem of calculus. Pretty straightforward, right? The integral from x star to xt of g prime of x would just be g of xt minus g of x star, plus and minus a constant. Okay? Do we know something about the size then of the right-hand side of this equation? What assumption did we make about g prime of x? For corollary 2, we assume that g prime of x was everywhere less than 1 in absolute value. That means that xt plus 1 minus x star in absolute value has to be less than the absolute value of the integral from x star to xt of 1 times dx, right? Since g prime is less than 1 everywhere. And what's this integral equal to? Well, that's just the absolute value of xt minus x star. So what we have here is that the absolute value of xt plus 1 minus x star has to be less than the absolute value of xt minus x star. All right, now let's consider some cases here. Let's assume for a second that xt is actually less than x star. In other words, this difference here on the right-hand side is negative. The absolute value turns it into a positive. If xt is less than x star, so that this difference is negative, the only way for the absolute value to be bigger than the absolute value of xt plus 1 minus x star would be for xt minus x star to actually be more negative, that is smaller than xt plus 1 minus x star, right? So if xt is less than the steady state, then we know that xt minus x star is more negative than xt plus 1 minus x star. Cancel, cancel, and we get that xt is less than xt plus 1. That's an important result, because what does that imply? That implies then that the sequence of xt's from 0 to infinity is increasing. Right? What do we just show? If xt is less than the steady state, then it follows from that xt is also less than xt plus 1. So the x's are rising over time. Anytime your x is lower than the steady state, the sequence of x's is going to be an increasing sequence. All right. So it's not hard to see that if we reverse this argument, let's make xt bigger than x star, then we're going to find that that means that xt minus x star has to be bigger than xt plus 1 minus x star. Cancel, cancel, and we get that xt is bigger than xt plus 1. In other words, if xt is bigger than the steady state, then what do we know about the sequence of x's? It is a decreasing sequence. Everybody follow that so far? So let's take a minute and just see where we're at here. We know that g prime is everywhere less than 1, an absolute value. And we've taken any arbitrary xt that's less than the steady state, and we've demonstrated then that the next period's xt, that is xt plus 1, has to be bigger, so the sequence is increasing. If xt is bigger than the steady state, the exact opposite is happening. The x's are falling over time. Okay, now I'm gonna claim here that there cannot exist another x value, let's call it x prime, that is not the same as x star, such that x prime is equal to g of x prime. And that's because, Tavoy, and this is going to address your question in a second, and that's because g prime of x is everywhere less than 1. So what I'm going to make the assertion that there cannot exist another steady state value of x. Let's call it x prime. That is where x prime is equal to g of x prime. And the reason is because the slope of g is everywhere less than 1 in absolute value. If that statement is true, then what must follow? If there's no other steady state, and any x above x star is going to cause x's to fall, and any x less than x star is going to be associated with x's increasing. If x star is the only steady state of the system, then what do we have? Then we have that the limit as t goes to infinity of xt has to be equal to x star. That doesn't have to be true if there's potentially multiple steady states or multiple fixed points, right? You could have a decreasing sequence of x and an increasing sequence of x converge to different steady states. But if it is true that there's a unique steady state here in this system, then we know that in the long run, xt has to converge to that x star only. And what I'm telling you is that we know there cannot exist another value of x that is a steady state here because of this assumption we've made about the size of g prime. Now, Tavoy, let me try to answer your question with a little graphical argument to illustrate this. Let me place on the horizontal axis here different values of xt, and on the vertical axis different values of xt plus 1. So what I'm going to do is I'm going to draw a two-dimensional graph that shows how xt is mapped into xt plus 1. I'm going to draw the function g. Okay. Now, first off, before we do that, if a steady state exists for this system, then we know that the steady state value of x must intersect the 45-degree line, right? Because the 45-degree line is the locus of points where xt is equal to xt plus 1. So here's a 45-degree line. That is a line that just has the slope of 1. If a steady state exists, it's going to be the point where g must cross that 45-degree line somewhere. All right. Now, let's just draw a candidate value of g that satisfies our assumptions. One in which the slope of g is everywhere less than 1. So I'm just going to draw one as an example here. And again, I'm a pretty crappy artist, so I apologize about this ahead of time. But here's an example. G of xt. The steady state is going to occur at this point, x star, right? And then this point on the vertical axis is also x star. Now you will notice something here. Notice that the slope of g in a neighborhood of the steady state is less than 1 in absolute value. What is the only way for this function g to intersect the 45-degree line at more than one location here? It would be if this function g somehow turned back up to intersect the 45-degree line up here, right? Like that. Or perhaps it turned down to intersect the 45-degree line here. So here are two other candidate possible values of the steady state. But why do we know that those other steady states can't exist in this exercise? We've made an assumption, and that is that g has a slope that is less than 1 everywhere. Well, the only way for g to cross the 45-degree line at any of these other locations is if the slope of g exceeds 1 in absolute value. Okay, so that's really, hopefully, Tavoy, that kind of answers your question.
Yes, sir, definitely. Yes.
To get stability in these systems, you've got to have the slope of the mapping between the state and tomorrow's state, that is kt and kt plus 1, be less than 1 in absolute value, right? In fact, if the slope is bigger than 1, let's do a really simple one. Here's the 45-degree line, okay? Let's say the mapping G is linear with a slope of less than 1 everywhere. Tavoy, let's say that our initial value of x is here, x0, right? What is the value of x1 going to be? Well, simply trace up to G and over, and that shows you what x1 is going to be. Well, how do we find x2? Well, we simply map x1 back over to the horizontal axis by tracing over to the 45-degree line, and then back up to the G mapping to figure out what x2 is. x3 then is simply going to be this point. You see what's happening here? Starting from an initial x0 that's lower than the steady state, it's going to move in this kind of stair-step fashion until you get to the steady state. A point that starts above the steady state is going to move in a stair-step fashion down towards the steady state. And so the system is globally stable because the slope of G is less than 1, right? Now, Tavoy, what happens if the slope of G is greater than 1? Let's say our initial x is here. And how do we find x1? Here. Where is x2? Back to the 45-degree line and down. So here's x2. What's happening? The x's are moving away from the steady state. Likewise, if we start with an initial value of x above the steady state, the dynamics are going to look like this. So this is a steady state of the equation. However, it is globally asymptotically unstable. It is a global repeller instead of an attractor. And that's because the slope of the mapping G is greater than 1 in a neighborhood of the steady state. So that's why, Tavoy, it's imperative that the mapping between the state and tomorrow's state be less than 1 and be less than 1 in slope in a neighborhood of the steady state. Otherwise, you're going to have these kind of explosive, unstable dynamics in a discrete time world. Does that make sense?
Yes, sir.
Okay. Everybody kind of have intuitive grasp about what's going on there? Unfortunately, the Solow model is not a linear mapping. It's a nonlinear mapping. And the properties of the model don't fit nicely into the assumptions of the corollary. However, we can still prove that the Solow model is globally stable by applying the same kind of basic logic to the proof of proposition 4, which is where I'm at now. Okay. Prop 4 says that let's assume that assumptions 1 and 2 hold. What are those again? Essentially, that means we're dealing with a neoclassical production function, right? So we have positive marginal products, diminishing returns to those marginal products. So the second derivatives are negative. In other words, the production function is strictly concave, and the production function has constant returns to scale. It's linearly homogeneous. That's assumption 1. Assumption 2 was what? The Inata conditions, which said that the slope of the production function was infinite for very small levels of capital and 0 for very large levels of capital. It tells us something about the behavior of the marginal products at these extreme points. The Inata conditions, hopefully you recall from a couple of classes ago, was essential in demonstrating the existence of an interior steady state equilibrium, okay? What about the stability of the Solow model? As long as assumptions 1 and 2 hold, then the steady state equilibrium, which we've already characterized in the Solow model, without technological progress, that satisfies the difference equation, right? Change in kt plus 1 times 1 plus n is equal to s f of kt minus delta plus n kt. This was the fundamental law of motion for capital. The level of capital per worker that satisfies this equation over time is going to be globally asymptotically stable, meaning that the limit as t approaches infinity of kt is equal to k star for all feasible initial values of capital. Doesn't matter what the initial capital stock is, we will eventually converge to the steady state. Moreover, there's one other small part of this proposition that I think is interesting, and that is that this convergence to k star is monotonic. What does that mean? The convergence is monotonic. That means if we start off with capital less than the steady state, capital is going to grow until it hits the steady state. But it's never going to overshoot the steady state and therefore have to shrink back. There's not going to be any overshooting, right? If the capital stock is above the steady state, the capital stock will shrink until the steady state is hit. It won't overshoot and then have to rise again to go back to the steady state. There are no cycles in the Solow model. There is monotonic convergence. Furthermore, what is implied by this result is that the speed at which the economy approaches that steady state is going to slow down as we get there. In other words, growth is really fast for countries that have a low level of capital per worker, right? Capital is going to rise quickly over time. But as we approach the steady state, growth is going to slow down and eventually converge to zero, right? It's kind of like that thought experiment you do where you say, okay, let me go halfway to the wall over there. When will I, and then take another step that's halfway to the wall from that point, and do that forever. How long is it going to take you to actually reach the wall? An infinite number of periods, right? If you simply go halfway there each single time. That's kind of what's happening in the Solow model. The closer you get to the steady state, the slower the transition dynamics become, which makes sense. Developing nations a lot of times will grow faster than developed nations. That's this idea of catch-up growth that's embedded in the Solow model, right? Countries that are already very close to their steady state, or what's called at their balanced growth path, tend not to grow as rapidly. They only grow to the extent that they can develop new technologies over time. Whereas poorer countries that are catching up with the rest of the world can grow quickly because they're adopting technologies, but also accumulating capital rapidly over time. It's the reason why countries like China and India, even though they're not as prosperous as the United States, have grown more quickly than the US for years now, is because they're in this kind of catch-up phase of their growth trajectory, whereas the US is a much more developed economy. The implication then, of course, is that China's economy will eventually slow down, as it already has demonstrated in the past few years. China cannot escape the logic of diminishing returns, okay? Okay, let's do this proof. And this will be kind of the main task for class today. So I've got, what, about 30, 35 minutes to do that. All right, the proof is going to proceed in a few steps here. The first thing I want to do is I want to establish I don't know what that noise is, but I guess I'll say I'm sorry for it, even though it's not my fault. It is a bit annoying though. Let's establish that the mapping G in this problem, which in the Solow model, G maps KT into KT plus 1, right? We just did a generic problem where we defined G as a function of xt. Now we want to apply that directly to the Solow model. Let's establish that G prime of K is at least positive for all possible values of K. Turns out we cannot demonstrate that G prime is less than 1 in absolute value everywhere. It's not going to be. And that's because of the Anata conditions, right? F prime is an infinite for very small values of K. And so because of that, you're going to have areas of the capital space where G prime is a lot bigger than 1. Nevertheless, we're still going to have global stability, and we can prove that. So let's establish that G prime is at least positive first. Okay, so the law of motion for capital in the Solow model can be written like this: KT plus 1 times 1 plus n minus KT times 1 plus n. So that's the change in capital between t and t plus 1, has to be equal to SF of KT minus delta plus n times KT. Okay, so KT plus 1 times 1 plus n, I'm going to bring the KT to the right-hand side and combine terms, is equal to SF of KT. Let's see, the NKTs cancel, and I'm going to be left with a plus 1 minus delta KT. Now all I have to do is divide both sides by 1 plus n. So S over 1 plus n times F of KT plus 1 minus delta over 1 plus n times KT. Let me define the function G as S1 plus n F of K plus 1 minus delta over 1 plus n times K. Now the function G in the Solow model takes this form. Therefore, kt plus 1 can simply be written as an explicit function then of kt, right, where G maps elements from the positive reals into the positive reals, and it's continuous by assumption 1. Since the production function is continuous and differentiable, G will also be continuous and differentiable. All right, because of that, we can simply take the derivative of G with respect to K, and what do we get? S over 1 plus n times f prime of K plus 1 minus delta over 1 plus n. What's the sign of G prime? Positive constant times f prime. What's the sign of f prime? Positive. The slope of the production function is positive. It's the marginal product of capital plus a positive number. Delta is a fraction. It's the depreciation rate. So G prime is positive for all K. Step 2 of the proof. Let's establish that K star satisfies our definition of being a fixed point. This should be very straightforward because we've already worked with a steady state of this model. We know by proposition 1 that S of f of K star minus delta plus n K star is equal to 0. Prop 1 established results about the existence and uniqueness of the steady state. And it said that the steady state value of capital had to satisfy this condition, right? F of K over K is equal to delta plus n divided by S, right? Or S f of K star minus delta plus n times K star is equal to 0. Let me add 1 plus n times K star to both sides of this equation. So S f of K star minus delta plus n K star plus 1 plus n K star is equal to 1 plus n K star. If I combine the terms here, you get, let's see, 1 plus n K star is equal to S f of K star, let's see, minus delta minus n plus 1 plus n. Well, these n terms are going to cancel, and you get plus 1 minus delta K star. Therefore, K star is equal to S over 1 plus n f of K star plus 1 minus delta over 1 plus n K star. In other words, K star is equal to G of K star. Therefore, K star is indeed a fixed point of our mapping G. Any questions so far? Tavoy, we good? Yep, okay. All right. The third part of this proof and final part then is to just establish that K star is globally stable. All right, now how did we do this for the proof of corollary 2? What was the trick that we employed? fundamental theorem of calculus, right? I think that's probably like the most important theorem you learn in Calc 1. We're going to do the same thing here. So we've got our kt plus 1. We're going to subtract k star from it. We know that has to be equal to g of kt minus k star. And since k star is a fixed point, k star is also equal to g of k star. So kt plus 1 minus k star is equal to g of kt minus g of k star. Okay, what's the right-hand side equal to? By the fundamental theorem of calculus, we can write this as the integral from k star to kt of g prime of k dk.
I can't really read that. I guess better.
Sorry, if I move the paper, sometimes it comes out of focus. And I've tried, Ben, this camera is, that's as good as it's going to get right there.
Hey Ben, can get to join the meeting?
Is the view better on the computer?
Yeah, it's very good.
Okay. Can the rest of you guys see the board okay?
Absolutely.
I should have sat closer. I'm good, that's why I sat closer.
Okay. I don't care where y'all sit. If you want to sit in an X'd out seat, that's fine by me, okay? Okay, so that's the integral from k star to kt of g prime. Well, remember there's this property in calculus where you can flip the limits of the integral as long as you multiply the integral by -1. So that's the same as the negative of the integral from kt to k star g prime of k dk. All right. Now, since g prime of k is positive for all k, we just established that in step 1, you'll recall. The derivative of g is everywhere positive. Then what does that mean? If g prime is positive, then when kt is bigger than k star, so let's take this one as the case we're looking at, where kt is larger than k star, then because g prime is positive, that means the integral has to be positive, right? And so that means that kt plus 1 minus k star is some positive quantity. So if kt is bigger than k star, making this whole thing positive, then kt plus 1 minus k star is positive, which of course means that kt plus 1 is also bigger than k star. Now let me make sure you guys understand the implication of what we're saying. Take a value of capital that's higher than the steady state. What we've just shown then is that next period's capital stock is also higher than the steady state. So what we've said here is that this sequence of k's is bounded below by k star. So if you take any kt bigger than k star, then the subsequent sequence of capital stocks has to be bounded below by k star. Now what happens if we take a value of kt that happens to be less than k star? Well, if kt is less than k star, then the integral is negative, right? Well, that just means that kt plus 1 minus k star is a negative number. And so this sequence then of kt's is bounded above by K star. So any KT bigger than the steady state means that the sequence is bounded below by K star. You're never going to get lower than K star. If KT is less than K star, then the sequence of capital stocks is never going to get higher than K star. It's bounded above. Now, we haven't demonstrated anything about whether or not these sequences are increasing or decreasing yet. That's the next step here.
So is K star just never attained?
Asymptotically it is, but not in the short run. You approach it, and then the epsilon between KT and K star gets smaller and smaller and smaller over time. So you do asymptotically converge to K star, but
But in like a practical sense, it's saying that like we don't actually get, like an economy doesn't actually reach there.
well, in the real world, where economies are hit by stochastic shocks all the time, then it's true. We're never going to actually reach a fixed steady state. But in a stochastic world, what we tend to see is we're going to fluctuate around that steady state in the long run, or that the distribution of outcomes ends up being stationary. That's the better way to put it. So we're actually going to look at a stochastic growth model later in the semester. And instead of a concept of a fixed steady state, the analog to that is what's called a stationary ergodic distribution, right? Where if enough time has elapsed, you can prove that the capital stock in any given period is going to be some element of a fixed probability distribution that kind of bounces around what the steady state would be in a deterministic world. But the distribution of different values over time can change until you get to the long run. It's convergence in distribution rather than absolute convergence to a specific point in the absence of any uncertainty. Okay, now you guys will recall that the fundamental law of motion can be written like this: KT plus 1 minus KT times 1 plus n is equal to S f of KT minus delta plus n times KT. So that's the law of motion for the capital stock. I'm going to transform this equation into something that tells us about the growth rate of capital. Because what I want to know is the following. If we're above or below the steady state value of capital, can we say anything about the growth rate of the capital stock? If we can, particularly if we can say if it's positive or negative, that's going to tell us whether or not capital is growing or shrinking. Okay? If we combine that with our understanding that there's only one steady state in this model, which we've already proved, then we know we should have monotonic convergence to the steady state. Let me divide both sides of this equation by KT. Then what do I have here on the left-hand side? I have KT plus 1 minus KT over KT. That's the growth rate of the capital stock. It's the change over the previous level. And that's equal to S over 1 plus N. I'm sorry, let's do this. 1 over 1 plus N times quantity S F K of T over K of T minus delta plus N. So here's an expression for the growth rate of capital in the Solow model. And this is true regardless of the value of capital. Now let me define for a moment, just so I can make this as clear as possible. This term that's in parentheses here, let me define that as just some h of KT. It's not G, by the way. It's just a different function, okay? What I want to know is, how does H behave as K increases? That is, what is the derivative of H with respect to K? What's that equal to? Well, we can take that derivative. It's going to be what? F prime of K over K minus F of K over K squared. And if I combine those two terms, I get a minus F of K minus KF prime of K divided by K squared. What's the sign of that? What is the numerator? F minus KF prime is the marginal product of labor, right? Which is the same as the real wage in a competitive environment, which is positive, over K squared, which is positive. So the whole thing is negative. So H falls as K increases. That is going to be very, very helpful for us. Why? What is the value of H at the steady state level of K equal to? That's S F of K star over K star minus delta plus N. What's that equal to? It's what? Zero, exactly. And so if K is bigger than K star, what's the sign of H? If H slopes down, and if H of K star is zero, then the sign of H for any K bigger than K star is negative. And the sign of H for any K less than K star is positive, correct? Let me say that again, make sure everybody, H prime is strictly negative. It slopes down. At K star, H is zero. So if we take any KT that's bigger than K star, H of KT is going to be a negative number because H is strictly decreasing, right? H prime is negative. If we take any KT less than K star, then that means H of KT is going to be positive. Why is everybody looking at me confused? I think that should be an obvious statement. What's confusing about that?
So it's just a maximum, right?
No, it's not. H is not a maximum. It's just a function of K that slopes down for all K, right? H prime we know is everywhere negative. So evaluate H at K star, and we know it's equal to zero, right? That's proposition 1. So pick any K that's bigger than K star, and that means H of K has to be negative. Since H prime is negative, it slopes down. Well, why is that important? Use that information to tell us something about the growth rate of capital. That tells us then that KT plus 1 minus KT over KT is going to be strictly positive for all KT less than K star, and it's going to be strictly negative for all KT greater than K star. Right? The growth rate of capital is some constant, 1 over 1 plus n times H of KT. H of K star is 0, and H prime is everywhere negative. So if we take any KT that is less than K star, then H of K is a positive number. And so the growth rate of capital then is positive. And what does that mean? That means the capital stock is increasing. So any KT less than K star, we actually have 2 results now. The capital stock is an increasing sequence, and it is bounded above by K star. If you take any KT that is greater than K star, however, H of K is then going to be negative, which means that the growth rate of the capital stock is negative. So capital is falling over time. So we have two things, that the capital stock is a decreasing sequence and it is bounded below by K star. For all KT between 0 and K star, what do we know then? We know that KT plus 1 is going to live somewhere on this interval, KT to K star, right? Take any KT less than the steady state. What do we know now? The sequence of capital stocks is increasing and it's bounded above by K star. So if we have some KT between 0 and K star, then we know then that KT plus 1 must be bigger than KT, but still less than K star. So the sequence KT is monotonically increasing. And bounded above by K star. The converse argument has to hold. Let's take any KT that's between K star and infinity. Let's take a big value of K. Then we know now that KT plus 1 is going to be somewhere between K star and KT. So that the sequence of Ks is monotonically decreasing and bounded below by K star. Take any high value of KT above the steady state. And we know that tomorrow's capital stock has to be less than KT, but it's going to be bounded, strictly bounded below by K star. Those are the two things that we demonstrated on the previous page. Now, if you take this information and we combine it, since K star is the unique steady state, then there exists no K prime anywhere else in the space of capital. That is, anywhere else in the union of 0 K star infinity. Anywhere else on the real line, such that KT plus 1 is equal to KT is equal to K prime. There's no other possible steady state or fixed point value for K for any T. Therefore, the sequence of capital must converge monotonically to K star for all possible initial values of capital. It doesn't matter what it is. Let's look, to make this as straightforward as possible, let's draw a picture. This is not a proof. It's just a illustration that helps provide some intuition. How do I want to draw this? Let me think for a second. I don't actually have this in my notes. Let's put KT here and KT plus 1 here, right? If the steady state value of capital is going to be the value that intersects the 45-degree line. What does the mapping from KT to KT plus 1 look like in the Solow model? That is, what's the function G? G, if you recall, was equal to what? S over 1 plus N F of K plus 1 minus delta over 1 plus N times K, right? What, can we draw that mapping in KT plus 1 space? Sure. What does it look like for KT very small? Well, for KT very small, F of 0 plus 0 is just 0, right? But how quickly is G rising as K gets bigger? Well, it's rising very rapidly because y f prime near 0 is infinite. So the mapping G is going to look like this, right? It's going to be increasing quickly. However, as K gets big, what do we know about f prime? It eventually goes to 0. And so what's the slope of G going to be for K close to infinity? Just 1 minus delta over 1 plus N, right? Because we have this linear term over here. So the mapping is eventually going to look like this. Where the slope is 1 minus delta over 1 plus N. Now, why do I know that this mapping G has to cut the 45-degree line at one place? 1 minus delta over 1 plus N, we know is less than 1, right? Delta is a fraction, so the numerator is less than 1. The denominator is bigger than 1. So that G function is going to slice through the 45-degree line at some point. That's where the steady state is. Now, take an initial value of capital. Let's start really poor. What's K1 going to be equal to? Well, trace up to the mapping G and over, and that tells us what K1 is. How do we find K2? Project K1 back onto the horizontal axis, and then trace up again to the G function, and that tells us K2. How do we find K3? Project K2 back onto KT space, and then trace back up to our mapping G again. And what do you see happening here? The capital stock is increasing, and what's happening to the step size bin as we get closer to the steady state? Okay, 0 to K1 to K2, these step sizes are getting smaller and smaller and smaller. There is monotonic convergence to the steady state. Notice we never overshoot the steady state. If we start off with a large value of initial capital, we're going to move to the left. And we're going to have fast growth or quick shrinking of the capital stock the farther we are away from the steady state. Growth slows down the closer we get to the steady state. That's this idea of catch-up growth in the Solow model. Developing countries grow quickly when they're in the early phases of their growth trajectory. And why is that? Because the marginal product of capital is big for poor countries. The returns to the first few units of capital are much higher than the returns to the millionth unit of capital. Once an economy has reached its steady state, what's the only way it can grow anymore? Through shifts in the production function up. That is, through technological advancement. And that'll be where we stop today, because in the so we're going to do one more class on the Solow model, but we're going to talk about how we reintroduce technological growth into this model. What we want to do is impose or introduce technological growth in a manner that is consistent with what's called a balanced growth path, with the idea that things like output and capital are going to be growing at the same rate in the long run. That's what we mean by balanced growth. Well, it turns out that in order to generate that feature of the model, technology has to enter into the production function in a particular way. We'll discuss the way it has to enter into the production function, and then we will prove that proposition. It's actually called Yuzawa's theorem, which is a very important result in economics. And it shows how technology must enter into the production function in order for the economy to generate stable, long-run, balanced growth dynamics. Okay. Now it turns out or it sounds like that's really restrictive on the way technology has to appear, but in actuality, if you work with things like Cobb-Douglas production functions, you can do these clever change of variables to make technology look like the right way. And there's several practice problems on your review questions that you can work that show how to do that change of variable. Okay, that's what we're going to do in the next class, is talk about technological growth, how we augment the production function with technology. And then we're going to state and prove Yuzawa's theorem. And then we'll be done with the Solow model. We'll move on after that in the next week to begin probably a 2-week discussion of overlapping generations models. Okay. Tavoy, was that better or worse today?
I would say much better.
Much better for Tavoy. All right, Tavoy, I'm gonna stop the recording and end the meeting. So look for an email from Nick, okay?